record a short video for my students, and I decided to use this opportunity to test my YouTube recording technique. So please uh, don't forget that the department provides some tutoring hours, and you can always send an email to me and we can meet via Zoom, and we continue to talk about thermal equilibrium. Here is the question I want to ask you. So please take a minute, just think about it before switching to the next slide with the answer. It's about ice and water. What do we know about ice and water? Well, we can transfer one into another. For example, we can transfer ice into water, but that transfer happens only at 0 degrees of Celsius. We call it melting. We can freeze water, make it transition from liquid state into a solid state, but this transition also happens at 0 Celsius. When that could happen? Well, we know, for example, if we take ice and drop it into warm water, in that case, ice usually eventually melts, but that only happens when we have a lot, enough warm water. What if we mixture ice and water and eventually we see that the temperature of all parts of this mixture is 0. Ice is at 0 degrees of Celsius, water is at 0 degrees of Celsius. In this case, there is no reason anymore for any heat exchange. So if the system is in a good thermally insulated container, nothing gonna get melted, nothing gonna freeze. In this state, this mixture might last forever. But again, it can happen only when all parts of the system is at this specific temperature, transition temperature, the phase change temperature. So it means the answer is 0 Celsius. And this is another review. The strategy which we have to use to solve any problem in thermal equilibrium starts from, well, analyzing a system, and we know how to calculate the amount of heat for each specific process. So this is an example of a very common situation when you just need to cool down your drink. You have a container and some amount of ice, and the question is, how much water do we need to make, in the end, just simple situation when nothing solid left, just water. And the number one question is always, how many processes should we count? Always, number one question. For that, of course, we need to read very carefully the text, every problem, analyze every word, and styrofoam containers, maybe like a cup, something like this. And we've got 50 grams of ice in it. And an ice is something solid. And the temperature of ice initially is equal to -5 degrees of Celsius. Basically, we just took it out of the freezer. So question is, how much water do we need to pour? Okay, water, something liquid, and we don't know how much. That's what we're looking for. But what we know is eventually we need to get left with water only at final temperature of 5 degrees of Celsius. The initial temperature of water is 20 degrees of Celsius. So this cup is thermally insulated, and it does not take any heat, and we have no any heating elements, so we could ignore the presence of this container. It only holds the mixture together. So basically, the container is not a part of this mixture, of this equilibrium situation. We only have ice, which is solid. But if we give an opportunity to it to gain, to absorb some heat, what's going to happen to it? Melt? No. What we know from a previous slide like this one. There is no water below 0 degrees of Celsius. No water below 0. That's only ice. But there is no ice, actually. No ice above 0. So if we start from ice at -5 degrees of Celsius, it can't immediately start melting. Cannot. It has to warm up slowly but surely until it reaches the melting temperature. So the first process we could count for is water should get colder, but the next one is ice should get warmer and warmer and warmer, but it cannot get above 0 degrees of Celsius. There is no ice above 0. The final temperature for ice, for solid water, is 0 degrees of Celsius. But what is happening next? It starts melting. Melting is an additional process. What is at the end of this process? At the beginning, we have solid piece of ice. But at the end, when all ice melts, well, we get water. But that water is not the original water. This is warm and it cools down. But this one, cold. This amount of water just came from melted ice. So, and it means it has the same temperature, transition temperature, 0 Celsius. But the final temperature has to be 5. So this cold water will warm up. Well, probably I should redraw my arrow for the warm water. So each arrow represents a specific process. The process number 1, cooling down, temperature change, delta T is non-zero. The process number 2, warming up, delta T is non-zero. The process number 3 happens at the constant temperature, 0 Celsius, 0. But of course, there is a certain amount of heat related to this process, but temperature remains the same. And finally, the process number 4, warming up again. So, how many processes? Each arrow represents a process, 1, 2, 3, 4. The answer is 4 processes. Physics is done. That was physics. That's what we need to learn. The rest, so physics. The rest is basically memorizing things, the use of our memory. We need to remember what specific relationships, equations, laws we need to know and apply to mathematically analyze that physics. And the last part is, of course, math. Not math. Math. Mathematics we have to apply to these equations to answer how much ice, right? No, how much water we need to pour. That's our final goal. So this slide is a part of our electronic textbook. Here you can read everything I said. And now let's do the second part, equations. So first I want to redraw quickly the diagram. You know, legally, you cannot solve any problem in physics without drawing a diagram. So ice warms up to zero, melting. We get cold water, which warms up. And this is cools down. The final temperature is 5 degrees of Celsius. How do I know? I can read the initial temperature, and let's call it the object number one. In each situation, of course, every problem-solving process starts from objects, but then we have to count processes. Objects have properties, processes have properties, and those properties described by equations. So the object number one is warm water, the object number two is cold ice, and there is a process number one, the process number one, then the process number two, then the process number three, phase transition from ice to water. This is technically the object number three. And now, see, we can confuse ourselves with these numbers. Object, process, object, process, process, object, and then the process number four, final warm. So, of course, in reality, all these processes happening at the same time. Small part of ice is melting and warm water is cooling down. And when a small part of ice is melted, we got cold water that immediately starts warming up. So it's not like one thing happens first, another thing happens next. So the initial temperature of water, which is object number one, is 20 degrees of Celsius because we have ice, and the initial temperature of ice, which is object number two, is a negative 5 degrees of Celsius because we have ice. The mass of ice equals 50 grams, and the phase transition temperature is 0 Celsius, and the mass of water is what we're looking for. We don't know that. So each process is either temperature change or phase transition. The process number one requires a certain amount of heat, Q1. Its temperature change, so the equation is heat for temperature change. The process number two requires a certain amount of heat. Well, heat could be positive or negative. In this situation, it has to be negative because when water is cooling down, it releases energy. But the process number two requires some energy because ice has to warm up. C2, specific heat of ice times mass number two, times delta T2. Delta T2 is temperature change number 2. And the process number 3 happens at a constant temperature. There is no temperature change, but there is melting. So we have to use latent heat diffusion and the mass, of ice. And now we have to make a decision, should we write a plus or a minus? Because for this equation, we have to choose the sign. Because melting requires energy, Q has to be positive, scratch of minus, it's just a plus. And finally, the heat number 4 related to process number 4, but the object number 3 is equal to specific heat. Well, specific heat of what? Now it's water. I could have written C3, but in reality, C3 is equal to C1, water, times mass. How much cold water do we have? Well, it all came from ice, so we don't lose matter. Exactly the same amount of cold water as we had, amount of ice, and finally, temperature change again, it will be positive. Now, so after remembering and writing down these equations, we have to write the next equation, the heat balance equation, which says if we add all these together, the result must be equal to 0 for the thermally insulated system. Heat exchange inside the system happens, but the total amount of energy of a system as whole remains the same. That's what insulation means. No heat goes in, no heat goes out. And well, now let's continue on the next slide. I will rewrite again. C1 M1 times delta T1 plus C2 M2 times delta T2 plus L M2 plus C1 again, but M2 times delta T, well, for the fourth process equals 0. Now let's start writing numbers. And remember, because everything is equal to 0, we actually can use mixed units. Well, again, let's see. 4,000 joules per kilogram Celsius times an unknown mass. Of course, we can just leave an empty space. We have to write something, and when we write, it's either a number or a letter symbol. If we know a number, we write a number. If we don't know a number, we have to write a symbol that represents that number. Delta always means final minus initial. Final is 5, and initial was 30 Celsius. Moving on, plus the next one, it was ice warming up, specific heat of ice, joule per kilogram Celsius, times mass number 2, 50 grams, times, remember that ice warm ups from -5 to 0, and then it melts. So final for the ice is 0 and Celsius, and the initial is 5, so we need to subtract -5, initial -5. So this is how we have to write it. Delta always final minus initial. Plus, next term, latent heat diffusion times, well, joule per kilogram times 15 grams, and plus, I wasn't able to fit it in one line. The last term uses again specific heat of water. It's about water, 4,000 joules per kilogram Celsius times, and for water, So this was from 20 to 5 degrees of Celsius. And this is from 0 to 5 degrees of Celsius. So final temperature is 5, and initial was 0. And the whole thing is equal to 0. The most important part is done, and physics is completely done now. Now I have to do mathematics, and I always, because again, the whole sum is equal to 0, we can cancel lots of things. I always start looking for zeros I can cancel. And then I can cancel 3 zeros everywhere from each term. Now let's see units. I can cancel first degrees, Celsius, 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 and now I can cancel joule per kilogram, joule per kilogram, joule per kilogram, joule per kilogram. So the only unit is left grams, and that will be the unit of this unknown mass. So now I can rewrite my equation. Well, 4 times the mass in grams times 5 minus 20, negative 15, plus 2 times 50 is 100. And I don't write grams anymore. I know it will be grams. Unit is gram. And minus makes it a plus. 5 plus 300 times 50, 3 times 5, 15, 2 zeros, 1 0. And finally plus, this is 4 times 5, 20. And the whole thing is equal to 0. Now, this is negative 60 times m1 plus feels like I missed something. Yes, I did. I forgot to write mass right here times 50. This is M2. I forgot to put it between C and delta T. So that's not going to be 20. That's going to be 20 times 50. That whole thing is equal to 0. So this is 500. This is 15,000. And this is going to be 2 times 5, 10 to 0,000 equals 0. Okay. Now, this whole thing is positive. This I can move over there. 15,000, 16,500 will be equal to 60 times m1. M1 will be equal to 16,500 over 60. So 1650 divided by 6. 275, and I remembered it should be grams. Well, I know I have a slide with the solution. Let's hope I didn't make any mistakes, and that should be the answer. And it is. Great job, everyone. So, this is the problem number 2, which is very similar, and I would ask everyone to make a snapshot and discuss this problem, but then solve it using strategy from problem number 1. But I'm done. I hope the strategy was explained clearly in all the details, but if there is some questions, please send me an email and I will answer. Thank you. Bye everyone.